Good morning. That was a nice introduction. Thank you for having us here. We are thrilled to be here and we are excited to share our journey with you. We just want to take a minute to quickly introduce Acresium before we dive into the core topics for today. Acresium is founded with the mission to empower the entire investment life cycle. And we do this with our data operations and analytics SaaS platform. Like we said, we manage over $650 billion of assets, world's most sophisticated financial organizations. We have over 1,600 plus employees in our offices in New York, London, Delhi, Bangalore, and Hyderabad. We manage TBs of transactional data and PBs of historical data. And I would also like to take a minute to explain the name Acresium. It's actually a combination of argon plus cesium. Argon is an inert gas. It emphasizes stability. Cesium is used in atomic clocks. It is precise. Being a data-first firm, it's very important for us that we have to be very stable and precise, and our choices do matter. Right? With that quick introduction, I will now move on to the core topics for today. So we'll first start with how we started looking into Postgres, why we chose RDS Postgres, and how we moved from RDS to Aurora. And just for context, RDS stands for Relational Database Service from Amazon. And then we'll also talk about how we are managing our Postgres instances, how we optimized costs of running, and the challenges we encountered and our learnings from there. And last but not least, we'll also talk about why we are moving from Aurora to Community PostgreSQL. And after that, we'll open it up for questions. So, we were running most of our workloads on SQL Server. And as our workloads were increasing and our business started to scale, we started exploring open source relational databases. We not only fell in love with Slonik because it is blue and cute, we also realized it's the most popular open source database. It's very advanced. It's obviously highly scalable, secure, reliable, robust, cost effective. When we were evaluating this, it was also the DBMS of the year, right? And being a financial services firm and the kind of data that we deal with, security was also really important for us, right? Postgres has a dedicated security team, and we could see that any time there is a potential incident or situations, the response was really effective. That gave us a lot of comfort for us. Of course, the permissive open source license and availability of Postgres on all major cloud providers also gave us the extra comfort to make sure that we can go ahead with this, right? And also, if you look at the number of commits or the number of contributors, that's something that has been increasing continuously year on year. And it's not while the only criteria, it's very clear that we are adopting something that is clearly evolving, right? And the community support is also something that we're really impressed with, right? The active engagement in the community. Like even if you look at the description of Postgres novice mailing list, right? It says every question is welcome, right? So that's an attitude that we really love and embrace. And last but not least, developer preference was also an important thing, why we started looking at Postgres. And we're not just talking about our developers, we're also talking about 2022 Stack Overflow survey, right? Interestingly, professional developers preferred Postgres over everything else that's available. While all of this is at play, right, and we decided that we're going to use Postgres, I would like to quote the standard POC joke, right? Like I just asked ChatGPT, tell me a POC joke, and the first thing it came up was, why did the developer go broke, right? and it says because he did not do his POC, right? So putting things into context, it's not an easy move, to kind of move a lot of data, and that to mission critical data, without a very strong backing, right? So we decided that, we'll do this POC mostly to understand how viable is our idea, right? And then any technical risks that we have to deal with, and most importantly, to get stakeholder buy-in and confidence, right? Which is very important for these sorts of initiatives. Then, we decided we'll pick up the top 20% load, right? Which is actually driving the 80% load on our system, because, it has to be done in a finite amount of time, right? So with that being done, the next step became obvious, like we have to first audit, log, figure out what that load is. We decided, two key objectives for the POC that we are doing, right? The first objective is whatever current performance that we are getting, we want to make sure that with Postgres, we are able to get that performance, right? The next thing is we are a growing firm, right? So it's also important to us that we can support the 10x workloads of what we are doing now. So that's the next criteria, right? So we also figured out how to generate the 10x workload. So with this criteria for success being clear, the workload that we wanted to use being clear, we then went on to the next steps, right? So we have all our data in Microsoft SQL Server, right? To do this test, first we have to configure a Postgres instance and figure out a way to move the data sets that we're interested in from SQL Server to Postgres. That's where we used a schema conversion tool. It's called SCT from AWS, because we have most of our workloads running on AWS. Right. So SCT was great for tables and indexes, but when we had to hand code, most complex views and stored procedures, and later on into the POC, we realized that even for tables and indexes, we had to, hand code, because write indexes were not being used in plans because the data types weren't matching. So, in case you're planning to do something like this, it's very important to review the output and make sure the data types are matching. So with schema sorted out, the next step was how did we migrate data? So we used DMS, or database migration service. Again, it worked well for small tables, but for really large tables, we had to use copy out and copy in, right? So with this step done, we had an instance, we had schema, we had data. Right. Now the next challenge that we had is we had to figure out a way to reproduce the workloads, our production workloads, on this new instance. And before we do that, we also had to fix our code to actually work with Postgres. So we rallied, and then we quickly fixed our code. Obviously, it was iterative, and then when we built this infrastructure, we also made sure that we can compare the performance query by query, right? So yes, we sized the instances appropriately. We made sure that we have this replay infrastructure, and we got it up and running. And then we started measuring results, right? This is where things got interesting, right? We could figure out some queries were doing well, and we had to work on a lot of queries, The session before PG hint plan also helped us to make sure that we got the necessary performance, right? The next step is we have to present the results and, make sure that we understand them. So we came up with a graph. Now this reminds me of a graph joke, right? So it goes like this. Why did scatter plot break up with line graph? And the answer is because it couldn't connect, right? So it's really important that what we are presenting connects, right? So we did not use scatter plot, obviously, so we used bar graphs. Again, just to make sure the aspect is clear, what we are presenting in x-axis is a factor, right? It tells whether Postgres was better or worse when compared to SQL Server. What we have on y-axis are the number of samples in each bucket. I'll take an example to make this more clear. So let's say we have a query that takes 4 seconds to execute on SQL Server. Say we have another query that takes 2 seconds. the same query executes in 2 seconds on Postgres, right? So obviously Postgres performed better here, right? So we divided SQL duration by Postgres duration, 4 by 2, that is 2, right? So we mapped this query to the bucket range 2 to 3. Like this is what you will see in x-axis. Conversely, if SQL Server performed better, say SQL took 4 seconds, Postgres took say 8 seconds, right? So in that case, we would represent the same thing. We divide 8 by 4 Postgres by SQL, but with a minus sign. So if you look at this graph, anything after 0 towards the right, that is where Postgres is performing better. And if you look 0 and left of 0 is where SQL Server is performing better, right? So again, this is not a general statement to say that Postgres will perform better, right? The point being, it is possible to optimize if you know your workloads and you know what is happening, right? Again, when we think about workloads, we had read-only, pure read type workloads, we have write type workloads, we have a lot of mixed workloads and analytical workloads. So I'll just present data for all of them, right? This graph that you're seeing is for read sort of workloads, right? The next graph that we had is for writes. Again, you could see that in most cases we managed to get better performance. And this last graph, right, is for mixed workloads. And as you could see, the number of samples are really high. Like this is one of the most used production use cases, right? Like, taking an example, like you could see that there were close to 3 lakh samples, right? Where the bucket range is 2 to 5 and, Postgres was actually performing better. So with this, we got confidence, right? That Postgres can actually work with our current production workloads. We then worked and made sure that we created 10x workloads, and even for 10x workloads, the results were pretty similar. With this, we concluded the POC, and it gave us the confidence that we can actually move to Postgres. So again, we made a conscious decision at that point that any new application which will be using relational databases will be built on top of Postgres, right? That's the key outcome of that POC, right? Then we had to make another decision, right? At this point, we were just getting started with Postgres, and from our company's perspective, what mattered most really was we spent time on optimizing the queries and we were getting the necessary performance. So we decided we'll offload the job of managing backups, doing patching to RDS, and then we got started with RDS. Now, as you can see, Srini is already here and he wants me to stop, and he would like to continue. So I'll hand it over to Srini to cover the rest of the topics.
Thanks, Mani. So the RDS PostgreSQL was doing great for us, but Aurora PostgreSQL is released, so we want to explore the new features available in Aurora PostgreSQL, and we want to use that Aurora PostgreSQL if it really matches to our workloads. So below are some of the interesting features which are there in Aurora PostgreSQL we have explored. So Aurora PostgreSQL, by default, the design itself highly available. The storage is spanned across 3 availability zones. So whatever the instance we create, it's just like a compute we are creating on the storage. The storage is by default, it's spanned across 3 availability zones, and it is replicated across the 3 availability zones. The availability zone is like a data center. So in each availability zone, we will be having 2 copies of the data. So total 6 copies of the data will be there. The next feature is auto recovery of the failed node. So at any time, if a compute node is failed in any of the availability zone, if at all you don't have any of the read replicas created, they will be able to create a new instance or else a new compute in any of the availability zone in 10 minutes. If at all we are having a read replica for that instances, the instance will become the new primary in 30 to 60 seconds. The next one is the copy and write clones. Let me take a step back here and explain this copy and write clones. It's really, let's take it as something like this. We have a source instance, or else a source Aurora PostgreSQL cluster is there. If at all I want to do a database copy from one cluster to another cluster, we generally take a backup and do the restoration. But Aurora has a feature where we can take a clone of the Aurora cluster and we'll create a new instance. Actually, this particular clone is also pointing to the same storage, whatever your source instance is having. So it means we are not paying for the storage. We are paying only for the compute power what we are using. Okay. So what if any of these instances make some changes to the data? So the changes will be occupying new storage. So we are paying for the new data changes what we made. So if at all imagine you are having some 100% of the storage is there, out of that we are not going to change 100% of data, right? So we'll be making some changes to 20 to 30%. So we will be paying for 20 to 30% of the storage what we have modified. That's the beauty of the copy and write clones. The next one is auto scaling of storage and IOPS. So like RDS, we no need to provision the storage in advance in Aurora PostgreSQL. By default, the storage is auto scaled till 128 terabyte. In the same fashion, the IOPS also. So we'll be paying for the IOPS whatever we use. It's like $0.2 for 1 million IOPS. The next one is the reader endpoint load balancing. By default, if at all we want to connect to a Aurora PostgreSQL instance, we have two kinds of the endpoints available. One is the cluster endpoint that will be always pointing to the master node. If at all I am having one and two read replicas, at any point of time, if the master is failed and any of the reader instance has been taken over as a master, so as we are using the cluster endpoint in our application, the cluster endpoint will always be pointing to the master node, so there is no need to change in the application code. It's like a virtual IP in our community PostgreSQL where we use any of the tools. And the next one is the reader endpoint. It will be always pointing to the reader nodes. So the reader endpoint will always be doing a DNS based round robin fashion load balancing to the existing reader nodes. If at all you are having 2 to 3 reader nodes are there, so your connections will be load balanced across the available reader instances. The next one is incremental backups. Whatever the snapshots, we call the backups as snapshots in AWS. So the snapshots are incremental. So even the manual snapshots also incremental snapshots. So we'll be ending up in paying for the storage what we have changed. So great, how we moved from RDS to Aurora PostgreSQL? It's very straightforward. We just need to create a Aurora read replica for the existing RDS instance. Wait till both the nodes are getting into the sync state. Once those are in the sync, just make the Aurora PostgreSQL as a primary. We have, like, while we are doing this migration in Aurora migration to Aurora PostgreSQL, we have faced a few issues related to stability. So if at all you are using the GAN and GAST indexes, so when you access the GAN index for the first time after you make the Aurora PostgreSQL as a master, it started taking more memory and it caused the instance reboots. That's a bug in Aurora PostgreSQL 9.6.6. So to overcome this, you have to migrate to 9.6.9 and then you have to rebuild the indexes. And the next one is increase in CPU usage. So as I said, like there is a dedicated process called Aurora storage daemon in AWS. So this is used to read and write the data from the disk. Okay, so to make the reads much faster, it will always try to read from the whichever is the nearest availability zone and it will get the data. So it will use your instance CPU resources to do the job. So there will be a slight increase in the CPU usage. Easily troubleshooting where the exact issue is there, which process is consuming, like which application is consuming more resources. So to do that, like we have built an infrastructure, our own infrastructure. So by default, Aurora PostgreSQL gives the performance insights. So we will enable this for each and every Aurora PostgreSQL instance. Also, we will give access to every user, including the developers. So if there is any issue, they will be easily go and check the whatever the current running queries and the resource usage of that. And the next one is we have enabled query logging, like whatever the top time consuming queries, we will be logging the queries. Also we have enabled the extensions like auto_explain. So this will capture the execution plans of the queries and the error logs. And we have enabled the pgstat statements. The next one is, in community PostgreSQL, if at all a particular query or else which query is consuming how much amount of the resource, what is the top resource consuming queries, it's very easy to find it out, because I can use a Perl script or else a shell script. I can run it in the PostgreSQL along with my PGStat activity table, and I can get the resource usage. But AWS is a managed service. They don't give the access to the underlying machine. So how can I find out which particular query is consuming how much amount of the resources, or else which database user is consuming the more resources? So to do that, like, we have enabled the enhanced monitoring. So in Aurora PostgreSQL, they have given a flexibility where they will export resource usage of the every process to the CloudWatch logs. So we have written our own automation where we capture those information and store it in a centralized database. So it will be having the process. Whenever you see in community PostgreSQL, the process is having a convention like the cluster name and the database username and the database name and what action it is doing. So we'll capture that information and we will find out which particular database user is consuming how much amount of the CPU and the memory. So by this, we are able to find out like which user is consuming more resources. So once we found that, like, which user is consuming the more resources, then there will be multiple sessions from that user. Out of that, which particular session is consuming more resources. So to do that, we are taking the PGStat activity history and we are storing that information. So we join these two metrics, like the process ID and the username, the details and the timestamps. And we will take the process ID from the PGStat activity and we will join these two details to find out which particular query is consuming more resources, and we will start working on that query very easily. So along with that, like, we are also capturing the database growth. So how much amount of the database size is. So we'll do the trend analysis, like whether the data, how much data we are adding up to our cluster, and also it is useful for managing the cost and stuff. As I said, like, we are using hundreds of instances. So it is very important for us to control the cost. So in Aurora, so we can't control the IOPS usage because we will be pay for use. So it is, so we are taking all the Aurora clusters, whichever is there in our AWS accounts, and we will be capturing the IOPS usage of those Aurora clusters into a centralized database. And we will be creating a dashboard, like which particular Aurora cluster is using more IOPS. And also we will be monitoring like what is the usage of the IOPS in a day. So we will be taking the patterns, like when we are using more IOPS and which particular instance we are consuming more IOPS. So by this information, we will be able to troubleshoot like which particular instance is causing more IOPS usage. So we analyzing our error log, PostgreSQL logs to find out like which particular queries are consuming more IOPS. So managing the Aurora cluster. So Aurora clones. So at time of doing the upgradations and the patching, we are using the Aurora clones to do this. Like as I said earlier, we create a copy and write clone. So we do actually upgradations and patching on that clones so that it will not impact our production. So we'll get to estimate the time, how much time it is taking to do the upgradations and stuff. So also to assess the performance, like after the upgradations and before the upgradations, how it is. So we use the PG replay tool to capture the workload on those instances, and we will replay the workload which we have captured from the logs on the cloned instances post upgradation. So by this, we will be assessing the performance before and after the upgradations. So with this, I hand it over to Srikanth.
Thank you, Srini, and thank you, Mani. So as Mani mentioned, we are not only a data-driven company for our clients, but for our own team as well as our organization. So managing Aurora is good, but what about the costs? So that's where Srini explained about the infrastructure that we built, which will help us understand analyzing the costs and make sure we take the informed choices. So I'll be covering mostly on the cost aspects in Aurora. So first one is AWS provides a billing aspect every month, but AWS also provides AWS Cost Explorer. which we can slice and dice based on the account, based on the region, usage type, etc., which will help us understand where we are spending the money, where are we going, you know, most of the cost aspect is going. So AWS Cost Explorer also provides recommendations, not exactly Cost Explorer, but rather AWS. They also provide the patterns, they also analyze the patterns, and then they provide the recommendations as well. For example, you might be under provisioning the instance types, or you have over provisioned the instance types. So such recommendations are also there inbuilt in AWS. But we also built our internal advanced infra so that we can be taking more advanced choices. For example, on a single Postgres cluster, we are running multiple databases. Now the question is, which application is consuming more cost, or which application is consuming more of my compute resources, or which is contributing to the anomaly? What if it's causing a noisy neighbor problem? So for such detailed infra is not there in-house built by AWS. That's where our automations will come into picture. So coming to the cost saving features, I'll be broadly covering on 3 aspects. One is on storage cost, the other is on compute, and then on IOPS costs. In the storage cost aspect, as Srini also mentioned in the earlier slides, there is a copy on write clones, which is a very beautiful feature in AWS. Let's assume that you have a production instance, and then say, for example, you have 100 terabyte of data. So eventually you'll be paying $10,000 per month. And for a high availability, let's say you created a reader instance. You have to pay another $10,000 if you don't have the Aurora, if you don't make use of the copy on write clones. And let's assume that you have lower environments. Let's say you have a UAT environment or dev environment. As and when you create a new copies, if it is not on Aurora, if it is not on copy on write clones, you will eventually end up paying more and more for the storage costs alone. So copy on write clones were useful in saving the storage cost in that aspect. And coming to the compute costs, we have reservation instances. Typically, like, it's a general practice to reserve for 1 year, and as per our analysis and observations, let's assume that you are reserving for 1 year, and you're doing it for 2 consecutive years on a 1 year basis. Whereas if you do the same thing for 3 years, you will be on the break even by the 2 years itself, meaning the 3rd year will be free of cost for you if you do it for 3 years. But the question might come, what if I'm running on a older instance classes? As per our understanding, AWS releases the new instance families rather, every 18 to 24 months. That's our observations by looking at last 4 releases. And even if it takes 2 years, let's say, we are already on the latest infra, so we are actually getting the additional 1 year free of compute costs. So that is an additional advantage that we made use of in our firm. And the other aspect is, like, as and when the clients are growing, as and when the infra is growing, if you want to make use of the newer infra for the more pods, like the older or dev instances can continue to run in the older infra. Let's say you reserve the instances, and then you might question, what if the new features came and then I want to make use of the better instance classes. So the lower environments can run on the older infra in such cases if you already have the reserved instances. The other aspect is on Graviton processors. So AWS came up with the Graviton processors. I'll be covering more details in the next slide, like how did we evaluate our performance on Graviton processors opposed to the x86 architecture. And coming to IOPS costs, in AWS, in Aurora specifically, the expected costs will be in linear in terms of storage and compute, whereas the IOPS costs will be very dynamic in nature. It depends on the usage patterns, it depends on the row queries, for example, might eat up a lot of IOPS costs, where we need, that's where we needed the inbuilt infrastructure to isolate and understand who is causing the problematic cost attribution. So we collect the infra based on pgstat activity. We store the information in a centralized repository. We look for the IOPS based wait events. That's where the cost aspect is coming. So I'll be covering a couple of wait events that we tuned and then we fixed in our environment. One is on IO data file read. Basically, as a part of RDBMS, it picks the read, it reads the data from disk and then put it in the memory. While this wait event is observed, it basically means that the process is waiting for the data to be read from the disk, which means either your shared buffers is not sufficient enough for the active data, which you can query based on buffer cache ratio basically, or index cache ratio. They are low on size. That is another indication that your shared buffers is not sufficient enough, and then you are actually incurring additional IOPS costs. The other one is it's a lightweight lock based on buffer mapping. So we have shared buffers. Within the shared buffer, we have buffer table, which basically means if your process is trying to access the shared buffer, it acquires a shared lock on the buffer table. And there are a couple of other scenarios where shared buffer mapping wait event will be observed, where, for example, if you don't have the block in the shared buffers, it means it is trying to read from the disk and put it in the shared buffers. So it takes an exclusive lock while performing this operation. Let's say based on the LRU algorithm, it's trying to clean up the block from the buffer itself, flushing out basically. Even in that scenario, there will be an exclusive lock. So these three scenarios are when this wait event will be observed. This also indicates that the wait events also indicates that your shared buffers is not sufficient enough. That's one possible cause. There can also be that your tables or your indexes are heavily bloated, because of which there is more churning out from the disk, and then the shared buffer is actually identified that it's a dead block and dead tuple, and then it's not making use of that information. The other aspect is where, let's say, you don't have a proper indexing strategy. So these are the three possible causes for these wait events, and our pgstat activity history helped us in identifying which instances at what duration are causing this. And like Srini also mentioned in the previous slides, we try to, like, even we have finite time, we try to optimize our times, right? We focus on the top consuming instances, top IOPS consuming instances, and then at what time they are going different from expectations, and then that's where we spend time. That's where this infra will come into picture. So few of the actions that we took were indexing. We enriched our developers also to make sure they have proper testing in our lower environments, and we also made partitioning as a good strategy so that we don't flush out on the shared buffers very frequently. So the other aspect is instance resizing. Like, there were a few instances where we were under provisioned for the workloads, and then we had to resize in such scenarios. Basically, as the data grows, as we are growing company, the instance resizing is also a factor that comes into picture. And then we had a scenario where instance resizing has actually helped in reducing the IOPS cost significantly. The price we are paying for the instance upsize is actually very less than the IOPS cost we were incurring. So, like, make sure you have proper sizing for your instances based on your workloads. That's our recommendation. And continuing about the Graviton processors. So Graviton processors are taken into picture by AWS. It's an AMD based processors, and basically they are energy efficient as well as performance cost efficient in comparison to x86. So again, we wanted to understand whether the Graviton process will be of help to us, and whether our workloads will be working properly on those. So again, we took the copy and write clones. We had simulated our workloads using PG Replay. PG Replay is very easy to set up. You just need to enable extended logging, and then you'll be done with it. So basically logline prefix, and then basically it captures all the queries that are run against your database except the prepared statements, and then we use the logs and then replay it on the target instance. So our observations based on R5 versus R6G. R6G is the instance family where the Graviton processors were introduced, and based on our observations, CPU is actually better performant for our workloads in R6G using Graviton processors, and whereas memory component were more or less same in both R5 and R6G, memory utilization I mean. And coming to the cost aspect, it was 10% cheaper, which is additional advantage to us. And then I would like to quote that this is for our workloads when we say CPU performant. I have also seen few other articles where it has claimed that R6G was less performant. So I would suggest you to test for your own workloads and make informed decision accordingly. And based on the test results, we migrated all of our Aurora instances to R6G, thus saving about 10% of the costs. The next topic is preparing for self-managed. So over the years, with our expertise running on Postgres, we built a good team, which now we can handle, and then we can upsize our challenges. We want to challenge ourselves as well. And basically, the question will come in how to migrate from Aurora to community Postgres or self-managed Postgres, right? So we have evaluated mainly a couple of open source technologies. One is based on logical application, and the other one is PG Logical 2. So there are a few differences that we observed between logical application and PG Logical 2. Mainly, PG Logical 2 also supports schema-based replication, whereas in logical application, it's the complete database. We can't pick and choose which schemas that we want to replicate. And then in PG Logical 2, we have DDL commands where we can replicate to the downstream instances as well. And we also can create event triggers so that in case a new table is created, and even that table will get propagated to the downstream instances. So the next aspect is high availability. Like, how do we make sure that when we go to self-managed, how do you make sure that we have the high available architecture built properly? So our backend remains same, which is streaming replication that is inbuilt into Postgres. And the question will be how to manage the automatic failover mechanisms. So we initially tested with the basic approach, like rep manager with keep LFD. So we don't have any other distributed configuration store. We wanted to try it simple. And that's one architecture that we tried. And the other one is with Patroni, where it won't be relying just on the rep manager. Like in rep manager, it is only relying on the local rep manager service. Whereas in case of Patroni, it's a template. Patroni runs on Postgres instances, and then they keep polling to the distributed configuration store. And we can also have additional features like callback scripts, or we can say using tags, we can even include sync replica or async replica. We can make sure that don't be participating in the master election process. We can use the tags in Patroni. And also, we can store our configurations within the Patroni etcd itself. We were using etcd in the configuration store, distributed configuration store. So we can make sure that there is one centralized place where we can manage all our Postgres configurations. Whereas in case of rep manager or PG auto failover, we have to manage it locally. And then if we change it in one instance, and then if we forgot it to change it in the secondary instance, that's when the failover happens, then it will be a problem in such scenarios. Coming to the backups, we made use of, based on our prior experiences, PG Backrest has good features. Basically, it supports the compatibility to S3 objects, or it has incremental backups, it has parallel backups. Unlike in base backup, it is only one thread, whereas in PG backrest we can have multiple processes, multiple threads. We also have asynchronous continuous archiving, meaning let's say the generation is too high, then we can also enable asynchronous archiving. And we also have encryption, we also have retention policies managed by PG backrest itself. So these were some additional features that we observed over the community tools, and I mean the inbuilt Postgres tools. Coming to monitoring, we made use of the open source project called PGWatch 2. It has very detailed advanced open source metrics to collect, whereas the only piece missing is the alerting mechanism. So it only collects and then shows the dashboards, whereas the alerting is something that you have to configure out on your own. And then, like we explained in our previous architectures, like we also collect our internal config. Yeah. So why are we moving to self-managed? As the data grows and the usage increases, our compute costs were expected linear in nature, whereas the IOPS costs were very standing out and very changing basically. And then there was one additional issue that we found is with limited local storage on Aurora, whenever there is. And there were a few interesting projects that we want to explore as we make progress on self-managed. Yeah. Thank you.